Hey guys, so today we will talk about the Incenter-Excenter configuration, and we will derive the lengths and the angles, in the various parts of the configuration. Also, there is a secret circle hanging somewhere, and we'll uncover that. Okay. So first, we will derive the lengths and angles in the incircle setup. So let's say we have triangle A. Let's make this paintbrush thickness smaller. A, B, C is a triangle, and you have the incircle in picture. Let's say the center of this incircle is I, the incenter, and let's say the point of tangencies are labeled as D, E, and F. Okay, so the key thing that we're going to use is that the tangents drawn from a point to a circle are equal in length. Okay, so now AF and AE are tangents drawn from A to the incircle. So they are equal. So let's label both of them as X. Similarly, we will label both BF and BD as Y, and CD and DE as Z. Okay. All right. So now we write down a system of equations in terms of the sides of the triangle. So X plus Z is equal to B. X plus Z is equal to B. X plus Y is equal to C, and Y plus Z is equal to A. Okay? Now if we add these equations up, you get X plus Y plus Z 2 times, each of them comes twice. On the other side you have A plus B plus C. Okay, A plus B plus C. Therefore X plus Y plus Z is A plus B plus C by 2, which is basically the semi-perimeter. So X plus Y plus Z is S. Now subtracting equation 1, let's label them equations 1, 2 and 3. If you subtract X plus Y plus Z, if you subtract X plus Z from X plus Y plus Z, that is, if you subtract equation 1 from equation 4, right, you get X plus Y plus Z minus X plus Z is equal to S minus B, okay, which is basically nothing but Y. Similarly, you will get X to be S minus A, and similarly you will get Z to be S minus C. Okay, so in fact, therefore, we can relabel these guys as X is really nothing but S minus A, Y is S minus B, and Z is S minus C. Okay. Alright. Now let's chase the angles in this setup. Okay. So now we're going to chase the angles. So here, for the angles, what we'll do is we'll take triangle ABC, okay, and we will join B to the incenter. Okay. Then we'll join I to C, and we will try to calculate the angle BIC. Okay, so let's calculate angle BIC. I claim, and I'll prove it now in a minute, claim angle BIC is 90 degree plus angle A by 2. Okay, when I say angle A, I mean this angle. Okay, alright. So let's see how to derive this. So to derive this, what we do is we label this alpha and alpha. We can do so because BI is the angle bisector. Okay, we use the fact that BI is an angle bisector, or rather is the angle bisector of angle ABC. Okay, we use this fact and we label ABI and IBC as alpha. Similarly, CI is the angle bisector of angle ACB, so we can label them beta and beta. Okay, now in triangle BIC, we know 2 angles already, we just have to find the third angle. So in other words, we have to find angle BIC is equal to 180 degrees minus alpha minus beta. Okay, on the other hand 2 alpha plus 2 beta plus angle A is equal to 180 degrees. This is just sum of angles of a triangle in the full triangle ABC. Okay, sum of angles of the triangle add up to 180. So if I rearrange this, I can get a formula alpha plus beta is equal to 180 degree minus a divided by 2, which is the same as 90 degree minus a by 2. Okay. Now I plug in this equation, this alpha plus beta is 90 minus a by 2 in the boxed equation. Okay, so what I do is angle BIC is equal to 180 degree minus alpha plus beta, but we already know alpha plus beta is 90 minus a by 2, so you get 180 degree minus 90 minus a by 2, right? And if you simplify this, you get 90 degree plus a by 2. Okay, so hence the proof is over. Okay, so this was the proof. Alright, so basically we know that this angle, so let's mark the angle here. So we know this angle is 90 plus a by 2. Okay, now something very similar happens in the excircle lengths and angles. Okay, it's almost similar. So let's in fact see how it works. So let's first chase the lengths. Okay, again we're going to use the fact that the tangents drawn from a point to a circle are equal in length. Okay, so let's label A, B, C. Okay, opposite to A, let's call it X, opposite to B, let's call it Y, and let's call this Z. Okay, alright. So now what we're going to do is we're going to label variables. Okay, so let's say BX and BZ are equal. Notice BX and BZ are both tangents from the point B to the X circle. Okay, so that's why they are equal in length. Similarly, CX is equal to CY, and AZ is equal to AY. Okay, that's again because they are tangents from the point A to the X circle, so they are equal in length. Okay, alright. So now let's write it in terms of the sides of the triangle. So what do we have? We have Z, okay, the length Z minus, so maybe I should write it in small letters so that it doesn't confuse with the capital Z that I've written. So let's call this Z. Okay, alright, so let's write it in small letters. So Z minus X is actually side C. As you can see, this is Z entirely, okay, and this is X. So if I subtract, what remains is the side opposite to capital C. So Z minus X is capital C. Similarly, Z minus Y is B, and X plus Y is equal to A. Okay, alright. So now what we can do is we can just add all the equations again. Okay, so let's try to add all the equations. Now X and Y cancel and you'll get 2Z on the left. On the right hand side, A plus B plus C you will get. And then if you simplify, you'll get Z is equal to A plus B plus C by 2. And this is nothing but a semiperimeter. So Z is simply the semiperimeter. A very useful fact to remember. So Z is just the semiperimeter. Okay, alright. So we have to now still figure out the remaining. So now that we know Z is a semiperimeter, it's pretty easy to figure out the others, because in the first equation, if I substitute Z is equal to semiperimeter, I'll get X is equal to Z minus C, but Z is S, so it's S minus C. Similarly, Y is equal to, you can just compute, it is S minus B. Okay, alright. So we have all the three equations now, so let me put it in a box. Here, X is equal to S minus C, Y is equal to S minus B, and Z is equal to S. Okay, so that's all the lengths. Okay, so let's write it here. So X is S minus C, and let's write Y here, S minus. Okay, alright. Now let's chase the angles. It's again very similar to what we did earlier. So I have joined the two, the vertex and the AX center. So let's label them A, B, C. This is the AX center, often labeled as I sub A. Okay, and I have joined B to I sub A and C to I sub A. We know that these lines, B I sub A, is actually the exterior angle bisector. Now what do I mean by that? Notice that in this triangle, this is the interior angle, and this is generally called the exterior angle. Okay, so the exterior angle is this guy, and BIA bisects that exterior angle. Okay, so since BIA bisects the exterior angle, we can label, let's say, this as alpha and this as alpha, and similarly CIA bisects the exterior angle, so we can call this beta and beta, and we can again use sum of angles in a triangle. So we can say the following, that alpha plus beta plus angle BI AC is equal to 180 degrees. Okay. Now we have to use the fact that if these two are alpha and this is 2 alpha totally, what remains is 180 minus 2 alpha. And similarly, this is 180 minus 2 beta. So let's apply this in triangle. So this, by the way, is angle sum in triangle BIAC. We can also use angle sum in triangle ABC, okay, in terms of alpha and beta. So the way we do it is angle ABC plus angle BCA plus angle BAC, which I'll just call A, is 180 degrees. But angle ABC is supplementary to the exterior angle. So it's 180 minus 2 alpha plus 180 minus 2 beta plus A is 180 degrees. I can cancel 180 and another 180, and you can simplify. You can write A as 2 alpha plus 2 beta minus 180. Right? This is what you can write it as. Okay, so let's write it in a more useful form by cutting off the 2's. So let's rewrite this, in fact, in another way. You could write it as alpha plus beta is equal to 180 degrees plus A by 2, which is the same as 90 degrees plus A by 2. Now, if you plug this into the original equation, we will get a formula for BIAC. So angle BIAC is 180 degrees minus alpha plus beta, the same as 180 degrees minus 90 degrees plus A by 2, which is 90 degrees minus A by 2. So in fact, this is the formula. Okay, so we have a formula for BIAC as well, and that is 90 degree minus A by 2. So now let's summarize whatever we have found. Okay, so the lengths in the incenter-excenter setup is the following. You have the full, now I've drawn both the incircle and the excircle. You have the triangle, okay, and AE, which is E's point of tangency of the incircle on AC. The length AE is S minus A. I have marked it, and similarly I have marked AY, which you know is a semi-perimeter, and I have marked additionally S minus B. Okay, now I claim that to really reproduce this whole configuration, the way you memorize this is that you just need to remember whatever I've drawn. You just need to remember the blue and the pink, okay, and you can derive everything else, including the green. Okay, so let's see how we can do it. So this I'm teaching you how to memorize it now. So all you need to remember is that this big line, right, this length of the tangent is the semi-perimeter, and you need to remember that this is S minus A. Okay, now let's see how by symmetry we can fill in all the others. Now if AE is S minus A, AF is S minus A, simply because both are equal in length, so we can figure that out. Notice the one the tangents passing through A is of the form S minus A. So by symmetry, BD and BF must be S minus B. Similarly, CD and CE must be S minus C. So I can write down all the lengths. AE is equal to AF is equal to S minus A. Okay. Then you have, by symmetry, you could write down BF is equal to BD is equal to S minus B, and CD is equal to CE is equal to S minus C. Okay. All right. Now AY is actually S. Okay, that you have to remember. However, notice if you know AY is S, since the side opposite to C is small c, what remains must be S minus C. So in other words, BY must be S minus C. Okay, because AB is C. Right? So S minus C is also equal to, okay, just BY. Okay, but then BY and BX are tangents to the excircle from B, so they must be equal. So that's also equal to BX. So CD is equal to CE is equal to BY is equal to BX is equal to S minus C. Very similarly, you can fill the remaining. So for instance, CZ is also S minus B by the same logic, and therefore CX also is, because CX and CZ are tangents to the excircle, they are equal in length. Okay, and finally with S minus A you can't do anything, but finally you could also write down, if you like, the fact that I said AY is equal to AZ is equal to S. Okay, so I've now filled in almost all the lengths in this setup. Okay, now we can also write down angles similarly. Okay, so just remember, so here there's a small little thing that I have written as 90, but we are not yet proved it. Okay, so let's see it in the next slide. But before that, what we proved earlier was that BIC is 90 plus A by 2 and BIAC is 90 minus A by 2. Okay. By the way, you could do the same thing on this side. You can join AIC and that would be 90 plus B by 2 and AIB would be 90 plus C by 2. Okay, by symmetry. So let me just write down all of them. So angle AIC is 90 plus B by 2 and angle BIC is 90 degree plus A by 2, and finally angle CI, okay, so angle, not C, angle AIB is 90 degree plus C by 2, and also angle BIAC as we derived it is 90 degree minus A by 2. Alright, now it turns out that angle IBA is 90, okay, and we'll see this now in the next fact. So you need the two key facts. In fact, the fact that this angle is at 90 really has nothing to do with the triangle. It has to simply do with the fact that whenever you have two lines, so let's see it down. Whenever you have been given two lines, okay, if there are two lines, okay, and you draw the angle bisectors, two different angle bisectors. Now what are they bisecting? So notice whenever you have two lines meeting, there are two angles. One angle is this one and the other angle is this guy. There are two possible angles, right? Notice that actually you might say there are four, but then these are vertically opposite and they are equal, and these guys are vertically opposite and they are equal. Okay, so essentially there are two angles. So there is this angle and then there is this angle. Okay, so the two black lines are bisecting those two angles. Okay, now the claim is the following. The claim is the angle bisectors are always at 90 degrees. Okay, so that's the fact I've written below. So the angle bisectors are always at 90 degree and it's very easy to prove. So let's prove it quickly. So since this black line is an angle bisector and bisects this angle, I can label both these guys as X and X. Okay, and similarly this guy also bisects this exterior angle, so I can label each piece as Y and Y. Okay, now notice, look at this line. Okay, if you look at this line, then X, 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 Y, Y, they all add up to a supplementary angle. So in other words, these are all 180 degrees. They form a straight line rather. Okay, so they are all supplementary to each other. So in other words, you get X plus Y plus Y, rather they all add up to 180 degrees. But that means 2x plus 2y is 180, which means x plus y is 90 degrees. Okay, but what is x plus y? X plus y is the angle between the two angle bisectors. So indeed we have shown that the angle bisectors are always at right angles. Okay, now we need another fact which is even more elementary, and that's the following statement. Statement says that if you have a triangle, right angle triangle BPQ, right angled at B, okay, then if L is the midpoint of BQ, then BL is equal to LQ is equal to PL, or in other words, all the three green line segments are the same. Okay, if you have a triangle PBQ right angled at B, in fact even the converse is true. Okay, so in fact the converse is true. This is actually a very easy statement to prove. All you need to know is the following fact. To prove the first, let's prove the converse. If PL is equal to BL is equal to LQ, why should triangle BPQ be right angled? Simple. If you keep a compass a center at L and you draw a circle, okay, if you draw a circle with L as the center and LP as the radius, then since it has been given that LP is equal to LB is equal to LQ, right, this circle will pass through P, B and Q, and what will happen is, since LP and PQ will become the diameter, PBQ will be right angles. Okay, so if BL equal to LP equal to LQ, if these three are equal, by drawing a circle with L as the center and LB or LP as the radius, you will see that PQ is the diameter and therefore PBQ is right angle. Conversely, if somebody gives you that PBQ, okay, is a right angle triangle, okay, then if you draw a circle with PQ as the diameter, then it passes through B because this is right angle, right? So if you draw a semicircle, okay, if you draw a circle with PQ as the diameter, it will pass through B because PBQ is right angle, and L will be the center of the circle, and therefore LB will equal LP will equal LQ. It's the same argument. Okay? Now I'm not writing that argument down because it's elementary, but essentially these two facts if we can use, and we can actually get our secret circle. Okay, so let's in fact get our secret circle using these two arguments. Okay, so here's the secret circle. If you look at the triangle ABC, okay, and if you look at the incenter I and the excenter IA, then I claim the secret circle is basically the following one. It's the circle, there is a circle passing through I, B, IA and C. Okay, the 4 points B, C, I and IA are actually concyclic. They are on a common circle. Why? The reason is the fact that we have proved before, that's fact 1. Notice by fact 1, this is 90 degrees, right? Because BI is an angle bisector and BIA is another angle bisector. Okay, and fact 1 tells you that whenever you have two angle bisectors, they always so if you look at these two angle bisectors, they are always at 90 degrees. Okay, so since BI is some interior angle bisector and this is the exterior angle bisector, they are always at 90. So IABI is at 90. Same logic we can use on the other side. So IACI is also 90. Okay, which means that if you draw a circle with IIA as the diameter, it passes through B and C. Okay, so a circle. Okay, so let me write the argument down. Angle angle IBIA equal to angle ICIA equal to 90 degrees from whatever fact, from fact 1. Okay, fact 1. And because of this, the circle with IIA as diameter passes through B and C, so we are done. Okay, passes through, this implies passes through B and C, and therefore IB, IAC are concyclic. So they are not just concyclic, we know something more actually, right? In fact, we know that IIA is the diameter, correct? So we know IIA is the diameter. So let's in fact draw I and C and get our cyclic quadrilateral, right? So we have a cyclic quadrilateral here and you can see the circle. In fact, IIA, okay, is the diameter with the midpoint L, the center of the circle. Now notice that this center L has one more secret nice property. Now let's see that property. If we join C and IL and B and L, right? B and L, since we already know from our excenter configuration setup that this angle must be 90 minus A by 2, right? We already know this is 90 minus A by 2. Okay, since this is already 90 minus A by 2 and this is the angle subtended at the arc, the angle subtended at the center will be double of that, right? So if I double that angle here, so since angle BIAC we already know from the excenter setup that this is 90 degree minus A by 2, angle BLC, L being the center, okay, we already now know that BICIA are concyclic and L is the center of the circle. Okay, so then BLC, where L is the center, will become 2 times 90 minus A by 2. But what is 2 into 90 minus A by 2? It is 180 degrees minus A. But wait, this angle is already A and I claim this angle is 180 minus A. This can only mean that A, B, L, C are concyclic. Or in other words, the circumcircle of triangle ABC, the circumcircle of triangle ABC passes through L. Okay, that's what happens because I just proved that angle BLC is 180 minus A. Therefore, angle BAC, which is A, plus angle BLC is equal to 180 degrees. So BACL are concyclic because this forms a cyclic quadrilateral. That means they are concyclic. Or in other words, in other more emphatic words, you could say the center of our secret circle lies on the circumcircle of triangle ABC. L lies on circumcircle of triangle ABC. Okay, so let's in fact see the I have summarized it. So the center of the circle, secret circle, lies on the circumcircle of triangle ABC. So here is the full picture. As you can see, I have drawn the circumcircle of triangle ABC, and as you can see, it passes through L. Okay, and the 3 green line segments are equal because they are all radii. So we got for free that LB is equal to LC equal to LI equal to LA. Okay, so we know that, let me write it here, the green line segments are equal. Li is equal to Lia is equal to Lb is equal to Lc. Okay, now this point L, by the way, can be located in various ways. Okay, so if you join A to I, one way to locate this L is, because you have proved this now, one way to locate L is join A to I and extend it until it meets the circumcircle of triangle ABC at some point, and that point is L. Okay, so one can construct this L directly by extending the angle bisector AI and meeting the circumcircle. Okay, that's one way to locate this L. And once you locate that L, LB equal to LC equal to LI equal to LIA. That's another way people remember this incenter-excenter configuration. Okay, this piece of the incenter-excenter configuration. All right. So now we have all the full picture in the final slide for you guys to see. So we know all aspects of this. We know that this entire length is S, from which we can compute this is S minus C. We should remember this is S minus A, from which we can derive everything else as well. Then we know these angles are 90 plus A by 2, and this is 90 minus A by 2, right? And we know that this angle is 90, as you can see, it's shown in green. And further, the center of the circle, these 4 points lie on a circle, I, B, I, A, and C. And the center of the circle passes through the circumcircle of triangle ABC. So this is the complete incenter-excenter configuration. Thank you.